Good. Well, thanks so much for inviting me to be here. It's my delight to be here. I've been in Korea only once before, and hadn't had a chance to visit KAIST that time, and so I'm really glad to be here. And it's of course a lot of fun for me to interact with Jay. Anyway, thanks very much for inviting me. I really appreciate it. I'm going to be here a couple more days, so if you want to chat with me personally at any time, please feel free to do so. Find me. I'm sitting over in where?
E2 building, third floor.
Third floor, yes, in the visitor office there. So what's the problem? The problem is biology is really hard. And it's been said that the 19th and 20th centuries were the centuries of physics and chemistry, but the 21st century is the century of biology. And in fact, biology, our knowledge about biology is absolutely exploding. The problem, however, is that that's not the first slide, is it? No, wrong talk. Wrong talk. Let's see if I can find the right talk. Oh, let's try this one here. Let's try. I'm not at FSU. This is a different talk. Okay, let's try again. I'm so glad to be here. So, what's the problem? The problem is that biology is the amount of data that's being collected in biology is absolutely staggering. With all the high throughput data that's being accumulated, data from all over the place. So the databases are growing exponentially fast, but we have really very little idea what to do with all the data. The parts list is nearly complete. What I mean by that is we know all the genes, but we have very little understanding of how they work. It's sort of like if I gave you the parts list for let's say an LG TV. Okay, so I give you the parts list and I say, what does it do? From the parts list, you would have a very, very hard time describing to me what that HD TV does. And it's even harder in this case. Even though we know all the genes, we have very, very little understanding of how they work. Much of what we know is correlative rather than mechanistic, historical rather than predictive, qualitative rather than quantitative. And what I mean by this is for example, if a person has a headache or a cold, they go to their doctor and their doctor says, take 2 of these and call me in the morning. And you have no idea if that's the right dosage or not, if it's going to work or is it not going to work. 50% of the time it works, 50% of the time it doesn't work. So we have these word stories about when things work, but we have very little predictive, quantitative ability to decide if things are going to work or not. Biological systems are incredibly complex, and understanding this complexity is quite challenging. I just put up here a wiring diagram. This is a simple wiring diagram for just metabolism of cells. Simple. Well, I mean, it's obviously not. But every node on this network or on this graph, every node is a different enzyme or a different chemical. And this shows how they all interact. And this wiring diagram is just one example of what's going on in a single cell. And it's incredibly complex and incredibly difficult to sort out. So why mathematics? Well, what we would like to do with mathematics is we would like to begin to address some of these challenges. We would really like to have predictive mechanistic theories to replace our verbal explanations. Just like Einstein was able to tell us equations for how the universe works, we would like theories that help us understand how biology works. We'd like to understand emergent properties. And what I mean by an emergent property is a feature of an organism or a feature of a system that is not the feature of the individual components. So you understand, for example, you might understand everything there is to know about a brain cell, a neuron, but you really don't know how the brain works, just because you know how the cell works. And so emergent properties are features of the organism or of the collection of things that are the result of the individual components working all together. You can look at an ant And you can watch how an ant moves, but you'll never understand how an ant colony forages for food. You can understand a cardiac cell, but you'll never understand why a person dies from a cardiac arrhythmia. So these are examples of emergent properties that we would like to understand. We'd like to understand unifying and transferable principles. And what I mean by this is there are many systems in biology that have very common mathematical features, and although the details can change, there are underlying principles, we believe, that we would like to understand. And this really is what mathematics is good at. Mathematics is good at seeing common features, and you learn how to solve one equation, and lo and behold, that same equation shows up somewhere else. And so the ability to solve, to do these things is transferable from one area of biology to another. And we would like to provide a view of biological behavior that's not available by other means. And what I mean by that, it gives us a vision of biology that you simply can't get from the laboratory, but you need a theoretical or a view of things. And this is what I think mathematics can and should be doing. And I think it is doing that, but this is what we'd like. Okay, so what's the problem that I'm interested in? I'm interested in cells. Of course, one could also be interested in organisms, but cells already provide a lot of problem. And so cells like bacteria or even your skin cells or your heart cells or your brain cells, there's already a lot of interesting things. And cells are all the time, they're all making decisions all the time. So cells have to make decisions about when to eat, when to move, when to divide, when to differentiate, when to grow, when to die. There are all these decisions that are being made constantly as they respond to their environment or as they do what they're supposed to do. There are decisions that are being made. And so a question is, how do they make decisions? As I say here, how do they do what they do? In the story I want to tell you 4 stories. And the answer in these 4 stories is the same. So the answer to the question of how do they do what they do is that in every single case, they use some feature of diffusion and some feature of positive feedback to accomplish the tasks that they're about to use. And so so I've already told you the story. The answer is that underlying many, many biological processes, there's a chemical reaction that involves some kind of positive feedback, and there is some kind of diffusive process. So those of you who are PDE people will hear the word diffusion. So there's some kind of diffusion process and some kind of chemical reaction with positive feedback that enables these organisms to do what they do. And so I'm going to tell you 4 stories, and if you heard these stories on the street, you would not think that they have anything in common. But what I want to show you is they do in fact have a lot in common in their mathematical structure. And so so you've heard my talk. That's my talk. But I have to tell you the examples. So what are the examples? I want to tell you about signaling in nerve cells. I want to tell you about cell polarization. I want to tell you about quorum sensing. And I want to tell you about cell size measurement. And these 4 different features. So to start, we'll jump back to all the way back to 1952 when Hodgkin and Huxley began or published their work on how nerve cells work. I really like this picture here. Hodgkin and Huxley worked on the squid giant axon, not the giant squid axons. It's really important that you get the order of the words right here. So it's a squid that had a large axon, not a giant squid. And so I put this picture. I really like that picture. In fact, this picture, I put this picture in our book. And actually, the day that I decided to put that in the book was one of my happiest days. I really like this picture because it has nothing at all to do with what Hodgkin and Huxley did. However, they worked on squid giant axon, and what they did is the following. So a cell, all cells are divided, have membranes that divide the inside from the outside. So they provide a barrier for flow of things across the cell wall. And that barrier is actually very much like a capacitor. It's a lipid membrane. and it acts like a capacitor in that it can segregate charge. So you can have a voltage difference across this lipid membrane because charge can be separated. So it's very much like a capacitor. And so what they realized is that you can write down equations deciding what the charge across here should be if you just treat it as an electrical circuit. So an electrical circuit diagram for this would be would have a capacitor, which is the membrane, and then you have some resistors where currents can cross across the membrane, and so you can write down a very simple Kirchhoff's laws for this, and the Kirchhoff's laws just say that the charges have to balance. So the rate at which the rate at which charge changes is exactly equal to the currents that come across there, just by Kirchhoff's basic law. Now, of course, the challenge then, these currents are in fact ionic currents. So sodium, potassium, and potassium and chloride, or leak current, are the main currents that move across this membrane. And so here you have the basic law governing how this works. Of course, the challenge is, how do these currents work? And it took a lot of detective work to figure out how these currents work. But it turns out that these are not just simple resistors. These are highly nonlinear resistors. And the voltage current diagram, or the voltage current relation for them, is fairly complicated. And in particular, these ion currents are governed not only by the voltage, but also by other variables which are called gating variables that turn on and turn off these currents. So the currents are highly regulated, if you wish. And so the equations that Hodgkin-Huxley wrote down were these equations, and they had details to all of this. But the important part of it is that the sodium current is something that is regulated by positive feedback. And so let me explain that to you. So the sodium current, it has a feature that the sodium current works as follows. So it's a channel. So current can move through the channel, but the current can it has gates that can open or close. And so, do I have it right? I think that's. Oh, they did it wrong. So whoever made that diagram got it wrong. So the way I do it is the following: it has gates that can open or close. Okay. So what happens is, under normal situations at rest, it has one gate that is closed and one gate that is open. This in Hodgkin-Huxley parlance is called M, and this in Hodgkin-Huxley parlance is called H. So this is normally closed, and this is normally open. Okay? Now, when the voltage goes up, if the voltage goes up, this guy opens up. So this is voltage sensitive. Okay? And so as the voltage goes up, this opens up. However, as the voltage goes up, this guy also closes. Okay? However, this guy works faster than that guy. So here's how Hodgkin-Huxley works. You're sitting at rest, and you give a little bit of current that causes the voltage to go up a little. That causes this gate to open. Now what that means is current rushes in. But current rushing in causes the voltage to rise even more, which is positive feedback. That's that picture right here. Positive feedback. So as current rushes in, that increases the voltage, which causes the currents to open more. So that's the positive feedback part of Hodgkin-Huxley. Then, as the voltage rises, slowly this guy closes and shuts off that inward current. And now you have an upstroke that is terminated because the voltage rises to a certain point, and this has terminated. Now other currents kick in and cause the voltage to go back down. And as the voltage is going back down, this guy wants to close, and this guy wants to reopen because of the opposite effect. And so what we've just done is the Hodgkin-Huxley Macarena, which is an action potential. So it sits here, it opens, closes, and then recloses, and then opens back up. And that's how the Hodgkin-Huxley works. And what does that do? That gives what's called the action potential. And the action potential is well known. It's exactly the spike in voltage that occurs when an action potential in your brain, and every neuron is constantly firing these action potentials, and it's governed by that positive feedback mechanism in ionic currents. So there you saw the Hodgkin-Huxley Macarena. Now you see that they got it backwards. Whoever did it this way, and I'm right-handed. I can't do that. So, but at any rate, that's the Hodgkin-Huxley Macarena. Okay, so that was discovered in 1952, and but of course they were working not just on cells, but these cells have spatial extent, and particularly they have axons. And so the voltage is not homogeneous along here, but in fact can be different at one point compared to another. And so they had to put in spatial variation. And the spatial variation turns out to be to modify the basic ionic current equation, and it modifies it by a diffusion-like term. And so this now looks like a diffusion reaction equation. In fact, it's a nonlinear partial differential equation of parabolic type. And the interesting thing is that you get a diffusion equation out of a voltage problem where there's charge and voltage, and that may be a little counterintuitive to you. Why do you get diffusion when you have voltage? And the answer to that is that think about where you get diffusion. Normally, you get it from something called Fick's law. Fick's law says that flux is proportional to gradients of concentration. But in fact, Ohm's law, which says that current is proportional to resistance times gradient in potential, is exactly the same form as Fick's law. It's exactly the same form. And so it's not surprising that if you get a diffusion equation for concentrations from Fick's law, it's not surprising that current equations should also give you a diffusion equation, because Ohm's law and Fick's law are exactly the same form. So diffusion in this context is not surprising from a mathematical perspective, because the underlying laws have exactly the same form. So while it's counterintuitive at first that we should get diffusion equations, it's actually not counterintuitive after all. And then what Hodgkin and Huxley did in a brilliant piece of work in 1952 is they showed that these equations had propagating waves. These propagating waves are traveling waves, action potentials. And this was a breakthrough discovery. The fact that nonlinear diffusion reaction equations can have propagating waves was a magnificent and wonderful mathematical advance. And since then, probably hundreds of thousands of papers have been written about this. I don't know if it's hundreds of thousands, but it's many thousands of papers have been written about the mathematics associated with. And it's now known that this is the fundamental mechanism underlying neurons, cardiac tissue, calcium signaling, dictyostelium, cyclic AMP signaling, muscles, and the list goes on and on and on of places where this is the fundamental mechanism underlying what's going on. Problem number 2, patterns in development. Turns out that 1952 was a very good year for mathematics, for mathematical biology, because Turing wrote his famous paper on morphogenesis in that year, and in his paper he noted that reaction and diffusion can be used to produce patterns. Now, it's still quite controversial how many different patterns are due to Turing mechanism, but it's been suggested that the patterns on zebrafish, the zebra stripes on an actual zebra, and shell patterns are all due to a mechanism of Turing. And I don't know if this is true or not. And in fact, it's quite controversial. Well, I want to show you one example that's not controversial at all. Of something that's related to a Turing pattern, and it's related to something called cell polarization. So the question is, how does a cell know where to go? So a cell is crawling. So for example, when you cut yourself, when you cut or get a cut, the epithelial cells have to go and they have to crawl into the wound and heal up the wound. So wounds heal up because the epithelial cells know where to go. They go in the right direction. They go toward the wound, not away from the wound. How do they know that? How do they know what direction to go? And I want to show you a lovely picture, a little YouTube thing. This is, let's see if I can make this full screen. Okay. So this is, oh nuts. It won't go away. This is a bacteria, right there. And this is a macrophage. So this is a white blood cell. It's in the blood, trying to find that little guy. Isn't that cool? So, it finally got it. So what it's doing is it's following this bacteria around, and what it's doing is it's crawling in the direction of this bacteria. And so the question is, how does it know how to crawl? How does it know how to do that? And what it's doing is it's sniffing the bacteria, but it's changing the location of its nose. So it's moving its nose around so that the nose is always pointing in the direction, and then it makes its pseudopods so that it goes in that direction. How did it do that? You might ask. Okay, so let's go to the next. So let me tell you a little bit the biology of cell polarization. Wrong way. Here we go. Okay. So it turns out that in the membrane of the cell wall of these organisms, there's a whole cascade of chemical reactions that take place. And in particular, there's a cyclic AMP is a signal that is often in the extracellular space. And then the cell has this membrane, and then intracellularly there's other chemicals that are activated. And so let me just walk you through this. So cyclic AMP creates a reaction on something called a G protein. It activates that. And then this guy activates something there. And then there's something here that comes along and activates this. And then this guy comes along and activates that. And this guy, when it's activated, has an effect on this, which activates this. And so anyway, there's a whole cascade of things that activate one after another, so that you get some activation process. And the end of the story is that this guy comes along and activates this. Now, what is this? This object, this activated A, is actually a molecule or an enzyme that causes actin and myosin to form structures. So it's a signal that says, build stuff here. So if A is built up in some place, then it's going to build its structure there. But the important feature of this is that this guy here has a positive feedback loop. In particular, A, which can live in the intracellular space, and A star, which lives in the membrane. A star recruits A to the membrane and activates it. So the more A star you get, the more A star you get, because there's this positive feedback loop here. And what that does is that gives us some kind of hysteretic behavior, which I'll show you in a minute. Now the second feature is that A star is in the membrane and A is in the cytoplasm. Now because A star is in the membrane and A is in the cytoplasm, they have different diffusion coefficients, because stuff that sits on a membrane diffuses slower than stuff that sits in the cytoplasm. So consequently, I have two chemicals that have different diffusion coefficients. So I have a reaction of something that can move back and forth between one space and the other, and two chemicals that have different diffusion coefficients, and that's what Turing said we should look for. So in fact, what we look for is we try to model this, and so here I write down diffusion reaction equations for this process. In particular, U, which is the active form, diffuses. Now I have theta here because I'm thinking of a circular cell and I'm thinking of stuff moving around on a membrane. So it can move around like this, can diffuse around, but it can react, and it can react with the stuff in the intracellular space. And it also has a circular diffusion coefficient. So I'm thinking of this as living somewhere in the inside and diffusing around. But in fact, they move back and forth between each other through some mechanism, some chemical reaction, which in this case turns out to have some kind of positive feedback. So here's the positive feedback, and here's the decay term. And so that this term just represents what that chemical reaction is. Very simple chemical reaction. It has this interesting shape. And so there's my system of partial differential equations. And I want to look at the ODE system. The ODE system without diffusion has this interesting switch-like behavior. That is, as I change the source, so the size of the source, I end up with this kind of a stimulus response. So increase the source and you see that you get a jump here in the steady state behavior. This is the amount of activated stuff. And so I have this very nice switch sitting in the chemistry. And now I couple that with the diffusion, and I find out that the PDE system has interesting behavior. In particular, the PDE system has two features that I want to show you. The first is the PDE system has hysteretic response to stimuli. So here's a little movie that will demonstrate that. So what we're going to see is you're going to see two curves. You're going to see a dashed curve, which is the stimulus, and then you're going to see a non-dashed curve, which is the response to that. And I want to demonstrate to you the response of this. So we go, and off we go. There's a stimulus and a little bit of a response. But you'll see that as this gets large enough, all of a sudden there's a very rapid increase because it has passed the switch. And then as this begins to decrease, you'll notice that it decreases, and this comes down a little bit. But as we get low enough, all of a sudden it collapses. But of course, that's hysteretic because the place where it turned on and the place where it turned off are different. So this has a hysteretic response to stimuli. If the stimulus is big enough, it'll put its nose there. If the stimulus isn't big enough, it won't put a nose there. And the second thing that this guy can do is it can respond to the location. And so, so in this simulation, I have a stimulus. And here's the response. So you can think of this as the nose. There's the stimulus, and there's the response. And let's see what it does. So there it is, stimulus, response. But now this guy is moving. And so the nose tries to follow, and it stops. And so it builds a nose there. And then this guy moves. And it just follows it right along and builds a nose where it needs to be. Okay? So this is what it's doing. There's this chemical reaction. It diffuses in the membrane, diffuses in the cytoplasm. It can move back and forth, activate. There's positive feedback, diffusion of different diffusion coefficients, and it has the ability to track stuff. So, what is this? Well, I claim this is an example of a Turing mechanism, or something like a Turing mechanism, in which you have an activator. The activator is the object, the excited stuff in the membrane. It diffuses slowly. The inactive form diffuses rapidly, and it leads to the stimulus response behavior. So what have we seen so far? We've seen that positive feedback with diffusion can give you signals, Hodgkin-Huxley. Positive feedback with diffusion can give you patterns, can give you shapes, and that's via Turing. Now let me show you some other things that can happen. But before I do that, I need to give you a little reminder about what diffusion is in the first place. So we all know that molecules move around by a random walk. So this is an example of a random walk, but you put a whole bunch of them together, and we know that they all spread out. And they spread out by standard diffusive process. And if I were to run this simulation, it would just show you can't find it. I didn't set it up correctly, but you know what the answer is. It's a Gaussian that spreads, right? Spreading Gaussian. So that's the solution of the diffusion equation. But the important thing to recognize is that in a very simple case where you have diffusion across a membrane. So for instance, I have two compartments, and one concentration in one and another concentration in another. If they're moving by diffusion, then in fact the flux across there is proportional to the difference in concentration. But it's also inversely proportional to the length. Now I want to point out these two very important things. You may not have thought about this before. But because the flux is proportional to the concentration difference, you do not have to count how many individuals are outside a region to know how many are outside a region. And the reason for that is you just watch the flux that goes out, and that gives you a measure of what's outside. If you know what's inside, and you know how fast things are moving, then you know how much is outside in a quantitative way. Because the more is outside, the less you're going to flux. So flux is a direct measure of the concentration outside. But also, flux is a direct measure of the length across which you're moving. So if you're moving slowly, you know you're moving through something that's very long. And if you're moving rapidly, you know you're moving through something that's very short. And so, in fact, there's quantitative information in this formula that can be exploited by organisms, and they do. And I want to show you how they take advantage of this very simple observation. So, flux is always from high to low concentrations. Fluxes decrease when length is large. And the key observation is that flux provides a quantitative measure of extracellular quantities without even having to think about it. So what's problem 3? Problem 3 is quorum sensing. Quorum sensing is the ability of an organism to know how large the population of organisms it's living in. So if I were to ask you how many people are in this room, but you're a bacterium, how would you figure it out? Okay? Now, we do it by looking around, but how do bacteria do it? And they do it. In fact, bacteria like Pseudomonas aeruginosa, they do it because Pseudomonas, they're the major cause of death in cystic fibrosis patients. What happens is they get into the lungs and they form a biofilm. And this biofilm colony grows, and biofilm is it's very hard to get rid of biofilm. But what they do is they will swim freely and they'll deposit themselves on a wall, say, but they do not become toxic and they do not become biofilm until the population size is large enough. So they avoid detection from the immune system when the population is small. But when their population is large, then they they differentiate and become different and start making biofilm. And so they have the ability to know how large their colony is. How do they do that? Turns out that almost all bacteria do some form of quorum sensing, and the question is, how do they do it? So, how do bacteria measure the size of their colony? Well, let me give you a clue. There's a chemical that they make, and the chemical is called homoserine lactone. But most people just call it an autoinducer. And this is a picture of biofilm. So this is a cross-section of biofilm. These are bacteria that are stained red. And there's a gel that sits around here that you can't see called exopolysaccharide. But this is the normal form of a biofilm. And here's a biofilm mutant. These guys do not make biofilm. And so you see the bacteria here are very highly compressed, very, very dense. But when you dump autoinducer on top of this biofilm mutant, it rescues this wild type behavior. In other words, it causes these things to start making exopolysaccharide. So autoinducer is the molecule that's made by the cell that is responsible for causing this form. And I have here, it's made by the cell and diffuses freely across the membrane of the cell. And that should, if you've been listening to my talk, that should be the clue. I have something that is made and something that diffuses. Okay? So, how is it made? So this, if you look up, Google it, you'll come up with this diagram, or at least something like this. And let me explain to you what's in that diagram. So there's some messenger RNAs. So that's a messenger RNA for a molecule called LAS-R, and this is an inducer, LAS-I. And these messenger RNAs make an enzyme or a protein called LAS-R and LAS-I. And LAS-I is the enzyme that makes our friend the homoserine lactone. It makes that. And then these two molecules come together, form a dimer. And that dimer turns out to be the promoter for the making of this messenger RNA. So this is the promoter chemical that makes that. And if you've ever taken a course in engineering at all, you'll notice this is a positive feedback loop. Okay? So you see that something is made that comes together and causes more of it to be made. So there we have our positive feedback loop. Now the second feature, and there are other things that go on which I don't want to get into, but if you want to write down an equation or equations describing how much autoinducer you have, and so you have to keep track of how much autoinducer you have inside cells and how much autoinducer you have outside cells, and so you do that very simply. And you realize that autoinducer is produced by the cell by some complicated formula, And on the other hand, autoinducer outside the cell, which I call E, is all it does is degrades, but the A is made by some complicated formula, which is from that diagram I had, and this guy degrades, but the other thing is that it can diffuse freely across the cell. So in fact, here's our Fick's law that says that the diffusion is proportional to the difference in concentrations across these. And here we have Fick's law for the difference in concentration. And if it comes out of A, it must go into E. And of course, there's a factor involving the density, because when concentrations move from one region to another region, they don't move as concentrations, they move as numbers. And so there has to be a volume factor that comes into that compensates for the fact that it's not concentrations that move, and so there has to be a number of cells per unit volume. And so indeed there has to be a term involving the volume or the density of cells. But anyway, we get a system of equations for how much autoinducer is in the extracellular space and here. And the important point is that flux out of the cell is related to the amount of E that's in the extracellular space. So the rate of loss of A is related to how much is out there. Now you make a simple model for this, and the simple model is to replace that complicated thing with something that looks like what's called a second order Hill function. So this is a second order Hill function, and this comes from the fact that it's a dimerization that's going on. And so those of you who know about chemical kinetics will realize that dimerization always gives polynomials of products which are quadratic. And so this growth rate can be modeled as this by this Hill function, and that leads to a very nice observation. I can teach this to my sophomore students in my introductory differential equation class, and we can understand it because it's just a phase diagram of a two variable system. And where you start, of course, with a phase diagram is you plot the nullines. And the nullines in this case are quite easy to plot, because the nullline for A is a curve which is here, and it has this cubic shape. And the nullline for E is a linear curve, a straight line, the slope of which is related to the density of the cells. So in particular, when rho is large, when rho is small, the slope is large, and when rho is big, the slope is small. So when rho is small, we see a slope like this, and then when rho is large, the slope is like that. And so now I can do a very simple, what's called a bifurcation diagram. And in particular, as I change between low density and high density, I see that the steady state of this change, and in particular, one gets a hysteretic curve. Now this hysteretic curve is very simple to explain, because at low cell density, the amount of autoinducer is very, very small. And at high cell density, the amount of autoinducer is very large, but there's this switch. And as the cell density grows, we move from having a small solution to 3 solutions and then a large solution. And so there is this density-dependent hysteretic switch that enables the thing to determine how much stuff is in the environment. This is exactly how cells count, through this switch. And it is important that this is a hysteretic curve. It's very much like a thermostat. It has the feature that it's hysteretic because you want to prevent rapid cycling. So in any room with an air conditioner or with a heater, your sets on a thermostat are always offset. The on rate is higher than the off rate, so that you don't do very rapid cycling. And that's exactly the same that these bacteria have. They want to prevent rapid cycling, because you don't want to start making biofilm and then stop and then start and then stop and then start and then stop. You want some mechanism to prevent the rapid cycling, and so indeed they have this hysteretic switch. And this is one of the minor successes of mathematics, because when we published this model, it was not known that quorum sensing was hysteretic. So this was a prediction. And so people went into the lab and checked it, and sure enough, it was hysteretic. So that was an example of a situation where a simple model told the biologists something that they hadn't known before, but in fact turned out to be correct. So this is a nice story. Simple story, actually, but actually rather nice. So what is the story? The story here is that the rate at which something is dumped is an indicator of the size of the space into which it's being dumped. So if I'm dumping something and there's not much capacity for it, it's going to back up on me. Whereas if I dump it and it goes out freely, there's not much there. So the rate at which something is dumped is a measure of how much stuff is out there. So I don't have to do a count, I just dump stuff. But of course, then when it backs up, it's telling me, there's a lot out there, and now the positive feedback loop can kick in and can make this explosion, and that's how one can make a decision. So this is a diffusion-coupled positive feedback loop which enables a hysteretic switch. Okay, so diffusion and reaction has enabled organisms to count. Okay, so where are we so far? Diffusion and reaction has enabled organisms to signal. It's enabled organisms to make patterns. It's enabled organisms to count things. And now let me show you one more thing. Diffusion and reaction enables cells to measure size. So an interesting question with fission yeast. Fission yeast grow and then divide, grow and then divide. This is what yeast do for a living. They grow, and of course they make alcohol on the side, which is one of the byproducts of their growing, and that's why we like yeast, because they make good beer or wine. But in particular, they grow and divide and grow and divide, and they grow until they get to a certain size, and then they divide. And so the question is, how do they know how big they are? So how do you know how big they are? So they have to have some way of figuring out how large they are so that they know to divide. So here's a picture of how these things work. So they grow, they elongate, and there's a contractile ring, and then they have to segregate their chromosomes. I mean, there's a lot of work going on in here, and eventually they divide, but the question is, how do they do it? And people have been studying the cell cycle for many years, and the cell cycle is regulated by chemicals, and the primary players in the cell cycle, primary player in the cell cycle is something called CDC2. Now this guy, CDC2, when it is activated, it initiates a cascade of things that leads to cell division or mitosis. But this is regulated by a positive feedback loop. In particular, this positive feedback loop is regulated by something called We1. And you can see here that it's a positive feedback loop, because if We1 is on this side, so We1 inactivates this, but CDC2 inactivates We1. So we have two negative connections, which is positive. So this negative plus that negative is positive. So there's positive feedback sitting in here. Now, this positive feedback loop is regulated by many, many things, but one thing it's regulated by is something called CDR2. Now, CDR2, you see, turns off We1, which means it's an activator of this guy. So this guy is an activator of it. But POM1 is an inactivator of CDR2. So POM1 keeps this guy inactive. So it inactivates that. Now here's the thing that's fascinating. POM1 is localized to the cell boundaries. This guy lives on the cell boundaries. This stuff lives in the cell nucleus. So they're physically separated. So we write this down. So how do you do cell size measurements? Well, the point is that POM1 lives in the boundary of the cell. All the other stuff is living in the center of the cell, at the nucleus. So when POM1 is close to the cell center, it has an inactivating effect on it. But when POM1 is a long way from the cell center, it can't work anymore, so it loses its ability to regulate CDR2. And so here's how you write this down. You want to keep the track of this amount of CDR2. That's this stuff. CDR2 diffuses, but so CDR2 diffuses and it degrades because so there's a dephosphorylation step here. but it becomes phosphorylated at the boundary by POM1. So you have a partial differential equation with a reaction term and a boundary condition where this stuff is being phosphorylated. So diffusion reaction with a nonlinear boundary condition. In addition, there are equations governing what this does. There's a system of ODEs that I wrote them down. But if you stare at this long enough, this looks exactly like Hodgkin-Huxley. Exactly in form, because you have a partial differential equation with some nonlinear terms here and some ODEs that are localized in space. Now, it's not quite this. It's not quite that, but it's very similar. And in fact, you look at these, stare at these equations for a while, and very quickly you find out that there is sensitive dependence on length in this problem. In particular, the amount of CDR2, which is the regulator of cell division, as a function of cell length, has an ultrasensitive switch. When the cell length is small, the stuff at the cell center is small, whereas when the cell length is large, the amount at the center is large. Consequently, you get a hysteretic response of CDC2, which is the mitosis regulator. And so cell length now determines the switch between inactivated to activated CDR2. So here's the story. As the cell grows, when the cell is small, it keeps a clamp on this cell cycle machinery. As the cell grows, there's a switch in which all of a sudden this becomes activated and it says, okay, time to divide. And so it divides and sets that mechanism off, and off we go. So the point is that the concentration of CDR2 at the cell center triggers this CDC2 activity, which leads to a length-dependent hysteretic transition to mitosis. Here are my 4 examples. What have we just learned? I hope we've just learned that diffusion, coupled with reactions involving positive feedback, enable cells to do a lot of different things. You arrange these things, it allows them to communicate, allows them to make patterns, allows them to make measurements, and make 2 kinds of measurements, counting measurements and length measurements. And in fact, those are the stories that I told you, but I could have told you several more stories. I could have told you how ants forage. I could have told you how the length of flagella and salmonella are determined. I could have told you a bunch of different things, and they all would have had the same underlying theme. There's some mechanism of diffusion, and there's some mechanism of positive feedback that enables things to communicate, to make patterns, to take measurements, and make decisions. And that's really my story. The mathematical description of these processes has a lot in common. This is an example of transferable principles writ large. Even though the details of the biology are vastly different, the mathematics is very similar. And so I think mathematics has told us something about how biology works. And I also think the study of biology has led us to important advances of mathematics. And that's what I wanted to tell you. And I have to tell you, however, this work is not done alone. I have a group of grad students who are very smart, and they help me out an awful lot. And I couldn't do this without them. And so with that, I'll thank you for your time, and thank you for listening, and entertain any questions you might have as well.